All right, guys, today we're looking at related rates. Related rates are the idea that we're going to take implicit differentiation and we're going to be looking at using that to find values and rates of things that are moving at the same time. This is our first true application day where we're looking at application of some of the stuff we've done. So ignore the 3 and 1 right now. We're just looking at the 5, just one situation. We have a 6-meter ladder is against a wall. If its bottom is pulled or pushed at a constant rate of 1/2 meters per second, how fast is the ladder top sliding when it reaches 5 meters up the wall? All right, so what we're looking at, and I'm going to draw my situation. We got our brick wall here. Here's the brick wall. We got our ground. Here's the ground. And we got our ladder. And we'll use a darker gray ladder. Here's the ladder. All right, it's saying that this ladder is being pushed or pulled at a rate of 1/2 meters per second. The ladder is 6 meters. And it's asking how fast is the top of the ladder, how fast is this part sliding down the wall, or it just says sliding, when it reaches 5 meters. So when this is 5 meters. Okay, so we're looking for this right here. Now with almost every word problem we do in this class, a picture is going to help you understand or better visualize what's going on. Now we create a very obvious shape here. This is a right triangle. We have a few different formulas that we know work with right triangles. But the thing is, we're looking for a formula that helps us find what we want. We want the rate of change in this side, right here. We only know 2 other sides and another rate of change. So it looks like we're going to be using all 3 sides. The only triangle formula we know that uses all 3 sides is Pythagorean theorem. So we'll call this A, this is B, and this is C. We have a squared plus b squared equals c squared. There's Pythagorean theorem. Now, this is where it turns into a calculus problem because we want to take the derivative of this. Now, if we look at this rate we have here, this is meters per second. So that means this is the derivative with respect to time. Well, there's no time in this problem. So when we go to take the derivative of a, it's 2a and then the derivative of a with respect to time. That's where the implicit differentiation comes in. Plus 2b dB over dt equals 2c dc over dt. So this is our equation. This is the one we're actually going to use to solve. So now let's start to label some variables. We have a, we have c, we can find b, but these 2 rates we don't have. This one right here and this one right here. Let's label this. Well, if we look, this is side A, and this is the rate that A is changing. So this side is dA over dt. That's the one we want to solve for. This is side B over here, down on this side, and we're looking for the rate at which B is moving here, so this is dB over dt. So that means this is 1/2. We know this is 6. We know this is 5. We're looking for this one, so it's fine we don't know that one. We need to figure out B and dC over dt. Well, let's go and figure out B first. B should be easy. It's just going to be this formula right here. We know A is 5, so 5 squared plus B squared equals 6 squared. So 25 plus B squared equals 36. B squared equals 36 minus 25, which is 11. So B is equal to root 11. So there's B, and that's technically meters. So B is root 11 meters. All right, so now we know B as well. What about dC over dt? dC would be the change in length of the ladder. And this is where you have to think about yourself, is the ladder actually going to be moving? Well, no, the ladder's sliding down the wall and being pulled away on the ground, but the ladder itself is not changing sides. So this part right here is 0. So now we can plug everything in. We have 2 times 5 dA over dt plus 2 times root 11 dB over dt equals 2 times 6 times 0. So that's just going to be 0. And now we're going to solve to get, dB over dt we know as well. So let's go ahead and get that. Times 1/2 equals 2 times 6 times 0. And now we're just going to try and get dA over dt by itself. So dA over dt equals the 2 and root 2, or 2 and 1/2 will cancel. So root 11 over 2 times 5 is 10 meters per second. Now here's the thing. We need to figure out, or should be negative. So we need to also take into consideration what a negative and positive means in this problem. We counted this as a positive because we counted the 1/2 as a positive because we said the ladder was moving away from the wall there. If it was moving toward the wall, that means this side, this green side, would be getting smaller. Anytime a side is getting smaller, the rate is negative. Anytime a side is getting bigger, the rate is positive. So in this case, it should make sense contextually. If you pull out this side right here, this side should get smaller. Okay? So we have a negative rate on dA over dt. If we were to push this side in, this side would get bigger. So a negative rate would be here, and we'd end up with a positive rate for dA over dt. Okay? All right. So more word problems like this. Let's just try another one. Water is flowing into a cone with a height of 16 centimeters and a radius of 4 centimeters at a rate of 2 centimeters cubed per minute. How fast is the water level rising when it is 5? And we'll just stick with 5 centimeters deep. Okay? So, water flowing into a cone. Here's a cone. Boop, cone, and I'll make it perfectly circle. There's some water level in here. Now, the cone itself, the whole cone, has a radius of 4 centimeters and a height of 16 centimeters. And we have water flowing in with a rate of 2 centimeters cubed per minute. Now, the 16 centimeters is not the height of the water. That's the full height of the cone. The height of the water is 5 centimeters that we're looking at. Okay, we need to keep that in mind. The reason this is important is because of what we're going to be looking for here. All right, we only are looking for the rate of change of the water level, which means we're going to be able to eliminate some things. So let's start with a volume equation. You need to know the volume of pretty much any shape that could be asked of you. Volume of a cone is 1/3 pi r squared h. If you don't know that volume equation, that's one to remember. All right, so there's the volume of cone. We have r squared and h. We do have an r and h in the problem, but we only care about the rate of change of height. We could go through the process of actually taking the derivative here and doing product rule, but there's a better way. If we look, every cone that we create with the water level will be similar to the cone of the hole because they have a shared angle down here. Since there's similar cones there, we can actually use a proportion to rewrite r and h. So we know that 16 over 4, that proportion is always going to be height over r. Or 4 is always going to be height over r. So what we could say is that r is just height divided by 4. No matter what water level we're at, your r is always going to be height divided by 4. What that allows us to do is rewrite this. Let me rewrite that. So that we're only dealing with one variable. So we have volume equals, and that's 16 times 3. Oh man, make me do some math. 8, 1, 3, 4, 48. Whew, that was tough. So pi over 48 h cubed is what we're looking at here. So volume equals pi over 48 h cubed. And now we have an equation that's much easier to take the derivative of. derivative of volume is the derivative of volume with respect to time, equals pi over 48 times 3h squared, and then this is implicit differentiation to still the rate of change of height with respect to time. Let's look at what variables we know. We actually know dv over dt. That's the flow of water in. This is dv over dt right there. The amount of water that is coming in. And we know this because it says centimeters cubed per minute. We know h. H at the time we're looking for is 5 centimeters deep. We're just looking for dh over dt, which is our last variable. So we have 2 equals pi over 48 times 3 times 5 squared dh over dt. And from here, we just solve for dh over dt. So I think we get 16 times 2, 32 over 25 pi. If I did my math right, equals dh over dt. And we always need to make sure we have units, so this should be centimeters per minute. Now, not all problems will be able to be proportionally set up like this, but we will have some, and they will be important for you to try out and try and do. Okay? All right, one more we're going to look at, I think. Maybe 2 more. Whoops, wrong button. Yeah, 2 more. Well, no, 1 more. The other one is the first problem on your homework. So, one of the problems on your homework. So we have this one. A winch, altitude of 20 feet. Okay, that means it's 20 feet out of the ground, water, whatever. Reels in a rope at 2 feet per second. How fast is a winch attached to a boat? I should probably say. Attach to a boat. There you go. Winch attached to a boat. Altitude of 20 feet. Is reels in a rope at 2 feet per second. How fast is the boat moving when the rope is, we'll start with 45 feet. Okay, so we have our water, and I'll put my little boat on the water here. We have, we'll say the winch is on a pier because it has to be 20 feet up. And then here's the winch. Winch just means a little wheel that wounds in the rope. So rope is attached there, and it's wheeling it in at 2 feet per second. Now the first thing we need to make sure we remember, this side right here, the winch side, the rope side, is getting smaller. So this should be a negative 2 feet per second. It's reeling it in. Means it has to be negative. It asks, how fast is the boat moving? So how fast is the boat moving along the water, this distance, when the rope is 45 feet, when this is 45 feet. All right, so once again, we got another triangle here. We'll say Pythagorean theorem, A, B, C. And we'll set up Pythagorean theorem again, A squared plus B squared equals C squared. And we'll take the derivative again. Hey, look, it's the same derivative. 2a dA over dt plus 2b dB over dt equals 2c dC over dt. All right? Now, let's go ahead and label things again. This is going to be dC over dt because it's the change in side C. That's side C. We need side B, and this is going to be dB over dt. Now, we also have a dA over dt in this problem, but notice A is the height of the pier. It's not changing. It's equal to 0. Okay? So the only thing we need to find first is we need to figure out what B is. So we have 20 squared plus B squared equals 45 squared. And at this point, we're dealing with a calculator problem. And so some of the problems in this unit will be calculator. And so we're just going to solve. B is equal to the square root of 20 squared, which is 400, 45 squared minus 20 squared, which is 1625. Don't think that's a perfect square. I could be wrong, though. It is not a perfect square. All right, so there's our B. This is feet. So now if we look, we know A. A is 20. Let's go ahead and plug it in. 2 times 20. And we know dA over dt, it's 0. Plus 2 times our b, which is square root of 1625, times dB over dt, which is what we're looking for. And if we do it correctly, it should come out to be negative because, as we said earlier, this side's getting smaller. So if we plug everything else in correctly, that sign should work out without any issue. Equals 2 times 45 times dc over dt, which is negative 2. All right, this is just going to be 0. We're just left with dB over dt equals, we'll say the 2's cancel. So negative 90 over square root 1625. This would, if it was a no calculator problem, this would be an okay answer, but this one would probably end up being a calculator problem. So we end up with negative 90 divided by that value, negative 2.233 feet per second. Okay. So the next 2 days are all going to be more review of this, so I won't have a video on anything else for this unit. It's just more practice with different types of problems. So just make sure you're in class or doing the homework online and seeing the different ways we could ask related rate problems. All right? With that, you're free to not do this anymore, not watch this video. Y'all have a great day.